Okay, so can you hear everything? All right, sounds good. Let's do it then. Okay, so this is another one of those little topics like Monte Carlo where you didn't really have to have this lecture so you could do your projects, but it's still something that's kind of nice to know about. And that's the whole business of visibility and color, which are two different subsets of what's called photometry. And so what's going on here is radiometry is basically what instruments measure. So preferably you're looking as a function of wavelength over very narrow wavelength bands, and you come out with some nice numbers that are in energy units of one sort or another. Photometry basically refers to what your eye sees. So your eye is looking at a very broad band of wavelengths, roughly 400 to 700 nanometers, and your eye is not giving you numbers in energy units, it's giving you a physiological sensation of something like color. And so basically the whole business of photometry is all about what you see, not what you measure with an instrument. And so what we're going to cover today is this general topic of visibility, which is, can I see something or not? It's that simple. And we'll talk about contrast. We'll talk about Secchi depth, where you're looking at this disk going into water until it disappears. We'll learn something about point and beam spread functions. So there you see something in the water and, it's visible in this case. And then after that, we'll talk about color. Yeah, Lydia.
Could we have the slideshow?
Oh, yeah, thanks. Here we go. Good idea. And then, so then there's the whole business of what is color all about. And with the exception of Emmanuel, you guys see a nice pretty butterfly here. And I guess he sees this like yucky looking butterfly, I don't know. Anyway, we'll mention what color is all about. There's a thing called a chromaticity diagram. There's a Forel-Ula index. When you look at the bottom of a hydrolyte run, if it covers 400 to 700, there's little tables of these things, and what do they all mean? Okay, and incidentally, I'm kind of into butterflies. I have this butterfly garden at home where I planted all of these different kinds of flowers that are all supposed to attract butterflies. And I get a lot of bees, and I think I've had like 3 butterflies. So the problem is butterflies like nice sunny meadows, and I live in a dark green damp forest. So I think it's like $500 per butterfly in my garden so far. So anyway, all right. So as I said, photometry is all about light measures or ways that you describe what your eye sees. And so the eye equivalents, if you wish, of radiometric variables are called photometric variables. And every radiometric quantity like radiance or irradiance, IOPs, AOPs, etc., they all have a photometric equivalent, which is what your eye would see as radiance, for example. And so, for example, the photometric equivalent of radiance is called luminance, and that corresponds to what we think of as how bright something is. Okay, so after the class, everybody want to go down and visit Alejandra and go snorkeling out in these nice crystal clear waters of Baja California. So you're out snorkeling along, there's little patches of coral and seagrass and whatever. So what animal do you see there? And is it dangerous? Should you get out of there or should you go over and play with it? You've seen the film, I can tell, no? Anybody see anything in there? Okay. Let's do the video. Oh, actually, I guess we can do it here. All right, here we go. Whoops, that's not what I wanted. Here we go. Need to see that one again?
Yes.
All right, let's back up here if we can. Whoops, let's hang on here. It really is astounding.
Oh my God.
That's crazy.
Oh wow.
Yeah. Octopus and cuttlefish are just amazing animals at camouflage. And what's interesting, like when an octopus or cuttlefish, like they land on this blackboard, they can turn the top skin to match what's underneath them. And it's not at all understood. How do they sense what's on the bottom and communicate that around to what's on the top? And there's some videos where they do things like they have a checkerboard pattern on the bottom of a fish tank, and you throw this octopus in and he's on the bottom and he sort of takes on a checkerboard pattern. It's just astounding. And then they can, if it's a smooth surface, they'll make their skin smooth. If it's a rough surface like this, they'll like wrinkle up their skin. They're astounding animals and not understood exactly what they're doing there. Okay,
Most of them have polarized vision,
yeah.
so they're better eyes than we do in terms of information.
Yeah. So yeah, a lot of people are really into studying octopus camouflage, and camouflage is sort of the flip side of visibility. You don't want to be seen. So anyway, who cares about underwater visibility? Well, the first person on record was Alexander the Great. And so the story is Alex wanted to go down to the bottom of the ocean and see what's going on. So he built some kind of, we would probably call a diving bell. It's not clear exactly what, but it had a window of some sort in it. And so he was lowered down to the bottom to take a look. And so the story goes is his wife and the boatman had a little thing going on the side. So they lowered Al down and they cut his chain loose, which you see hanging here, and they figured, well, we're done with this guy. But anyway, some way he got out, he made it back to the surface, and that's the story there. So he had numerous wives, so I'm not sure which one this was, but anyway, here he is on a Greek postage stamp, and here he is on a painting from, it doesn't say when, but Middle Ages sometime. Okay, so he cared about underwater visibility. Every Navy in the world cares about underwater visibility for diver operations, for hiding submarines and things like that. And when I put this talk together, I spent a long time Googling around for images of submarines like this one. And there is not one single image of a military submarine underwater to be found on the web with a Google search. Not one country. This is a commercial sub of some kind here. So it's pretty obvious that they don't let people take photographs of what their submarines look like underwater. But this is a really big deal. And Ken used to be at the visibility lab at Scripps. He was not at the radiometry lab. He was at the visibility lab because the Navy was very concerned with underwater visibility, and they had some embarrassing things happen, like they lost a submarine out in the middle of the Atlantic and they couldn't find it, literally couldn't find it. So they started putting a lot of money into underwater visibility back in the 60s. And that's why these guys like Petzold were funded to measure volume scattering functions, for example. Okay, dolphins care about visibility. Here's an amazing photograph of dolphins underwater being illuminated by bioluminescence that's triggered as they swim. It's astounding. Need I say more? The same thing happens to submarines. They don't like you to see submarines underwater with bioluminescence if you're flying over. Swimmers care about it, divers care about it, marine archaeologists, and The Creature from the Black Lagoon. If you haven't seen that movie, it would be a good way to spend next Friday evening, is see if you can find that on Netflix or something and stream it. So anyway, the creature was always almost about to grab the young maiden here, but she would always like get out and get on the boat or something just before he grabbed her. And I remember, I think this is from 1954 or something like that. And I saw it when I was like 8 years old, and it scared me half to death, you know. So, good movie though. Here's what it's like in China. So there's a guy, Liu Bolin, he's called the Invisible Man, and he has this crew that paints him up to look like a background. And then he just stands there and watches people go by to see if they see him or not. And when you go grocery shopping in China, there he is, there's the feet, almost invisible, because he has managed to just perfectly match his background and basically become invisible. So it's astoundingly good stuff. So you Google that guy, you'll come up with a lot of pictures of him doing things like this. And, you know, people just walked in, reach out to grab the tomatoes there. It's like, whoa. It's even better than watching cat videos. Okay. During the First World War and a little bit in the Second World War, they painted ships like this. It was called razzle-dazzle camouflage. And you would think that would be the stupidest thing you could do, was be to paint a ship to make it like stand out like that. But what was going on was, here's a ship viewed through a submarine periscope. This one, you look at it and you say, oh yeah, the ship's going this way, you know, it's obvious where I should aim my torpedoes. When you see that, it's so confusing. You can't even tell what direction the ship's going. So it greatly increases the number of misses by submarines shooting torpedoes at these ships versus these. And so that was very common in the First and then in the Second World War. And now, of course, torpedoes are smart enough, you don't actually aim them by eye. But yeah. Yeah, well, I was on a Navy SEAL thing one time in San Diego, and we're on this Navy SEAL boat deal going through the harbor, and we kind of came around this little point thing, and there was another Navy SEAL ship or boat. I mean, the boat was like maybe 40 feet long or something, 10 meters, whatever. It was painted like that. And I'm sort of sitting on this one boat, and I go around the corner, and it was like 5 seconds, and like, oh, that's a boat over there. I just, like, my brain did not record that that was a boat tied up to the dock. And of course, with 5 seconds before I recognized it, I would have been dead 4 seconds ago if this had been for real. But it was amazingly effective. Your brain just doesn't check that, oh, there's a boat over there. Okay, so anyway, visibility will get classified in various ways. One of them is detection, which means I can see there's something there, but I can't tell what it is. So just something in the water, I don't know, is it like a fish or a diver or, you know, a submarine or what? So that's, I've detected it. I can classify it, means, oh, I can see it's like a fish, it's not a scuba diver, but I can't tell you what kind of fish. Maybe it's a small fish up close, maybe it's a big one far away, I'm not really sure. And then there's identification, which is, oh yeah, I can see exactly what it is. It's a great white shark, and this is my last photo. So anyway, you'll see these things referred to that, like, people will have detection algorithms, they'll have classification algorithms, and so forth. Okay, just a matter of terminology you need to know. Environmental effects, or the environment affects visibility in different ways. So you've got absorption, scattering by particles, scattering by turbulence. So here, if we have a lot of absorption in the water, but not much scattering, what will happen is the image will just fade from view, but it doesn't lose its sharpness. It just becomes too faint to see. If you have a lot of particles in the water that are scattering light, that will take your image and it will kind of blur it out like this. But the image remains steady. It doesn't twinkle or anything. And then if you have turbulence, what will happen is the image may stay bright, but it'll be broken up by, by the twinkling. So when you're looking at a star at night and it's kind of twinkling, you're looking at atmospheric turbulence messing it up. If you go out on a hazy day and you look across the way and it's kind of hard to see what's going on there, that's usually scattering by atmospheric particles. And then maybe if it's a foggy day or something, maybe you'll have this case. So we're not going to go into that anymore in detail here, but just keep in mind that depending on what dominates the propagation through the atmosphere, you'll get different effects on whether or not you can identify something that you're looking at through the atmosphere. Okay, so now there's a little thing called the radiance difference law. We're going to want to see if we can see this thing, let's say 10 meters away in the water. So we've got an object here, that's our target, and we're over here with our eye or a camera, whatever it happens to be, and we want to know, can I see this thing in the water? So we're going to assume that the object is illuminated by ambient daylight, and we're going to assume that the radiance leaving the target does not significantly affect the ambient radiance. So this thing is not a bright light, for example. It's just sitting there reflecting sunlight. So there's two directions. I called it the C hat from the target. That's the light that's going to come from the target to me. And then there's the light from the background right next to the target. And that's going to go over, and I'm going to see that. And of course, along the way, this light's going to be absorbed. It's going to be scattered out. There will be scattering into the beam. That's all governed by the radiative transfer equation. And finally, the light from the target at distance 0 will get over to me at distance r away. Same thing for the background. It's going to start out with some background radiance here, and some amount of that will finally make it over to me. So we're going to assume that these two paths here are basically parallel. They're just right next to each other. And that whatever absorbing and scattering is going on for one beam happens to the other one. So they're close enough. They have the same IOPs. Okay, so now we want to figure out, what's going on here with these two radiances. Well, okay, so there's the radiative transfer equation. And I'll just write that as the d of L with respect to distance here, and this could be optical distance or horizontal distance, and the cosine would be 1. But anyway, so the derivative of the radiance with distance, and there's our beam C times the radiance, and then we have the path integration term here, and we'll assume there's no, actually it doesn't matter if there's internal sources. So anyway, we can write each equation like this, where this is for the target radiance, this is for the background. Now the catch is to say, well, look, if I group, this term and the source term here, let's call it L star, that's the same for both paths, because this has all the scattering into the beam, the scattering out of the beam, and so forth. So this and this will be the same for each path. And of course, beam C is the same for each path. The radiances themselves are different. Okay, so you say, well, look, let's just subtract one equation from the other, and these two terms will subtract out because we're getting the same scattering into and out of each beam. So we subtract those, we get the target minus the background. Now it becomes just beam C times the target minus the background. And if we just, here's a dl dr equals minus cl, well, that just integrates to the difference in radiances at distance r is the difference at distance 0, e to the minus cr. And if c is not constant along the way, it's an integration. If the water's homogeneous, then this is just e to the minus cr. So what we have is that even though the radiances themselves are different and they're governed by the full-blown radiative transfer equation, the difference in radiance is just governed by e to the minus beam attenuation times distance. So this is called the radiance difference law. So the difference in the radiance, all you have to know is beam attenuation. To get the actual radiance values, you have to know the full volume scattering function and solve the radiative transfer equation. So it's kind of a neat result. Okay, so then that's all radiometry. So now we want to turn this into something that your eye sees. And this gets us into this thing called luminosity functions. So what's called the photopic luminosity function basically is the relative sensitivity of a normal human eye to light of different wavelengths for bright light or daytime illumination. And it looks like this. So here's this non-dimensional Y bar, it's called. So 0, you can't see anything. 1 is it's relatively the brightest. So during the daytime, your cones are seeing color, and your eye is most sensitive out here at somewhere around 550 nanometers in the green wavelengths. And then back at 350, you don't see anything. At 750, you don't see anything. So you can get a UV laser and look in your eye, I don't see anything, but then you cook your eye. And that's because back here you're not seeing anything even though there's energy there. And here with this 532 nanometer laser, it looks quite bright because we're right out here, and this is very easy to see this green light. At nighttime, it's the scotopic curve, which is the rods in your eyes. They're much more sensitive. They're about 3 times more sensitive to seeing faint light, but they only see basically in black and color, the way your brain, they're sensitive to a range of wavelengths, but your brain turns that into a grayscale image. So anyway, the way it works is this is basically the sensor response of the eye. So to take a radiance here, which is in watts per square meter per steradian per nanometer, and turn that into what we call luminance or brightness, you take the radiance, you weight it by this photopic luminosity function, which describes how your eye is sensitive to this. You integrate all over all wavelengths, or in practice like 400 to 700. And then there's this funky conversion factor of 683 lumens per watt. And that's called the maximum luminous efficacy. That's a word you'll need to know at your next cocktail party. It's like, oh yes, we were talking about maximum luminous efficacy, and people will think you're really smart. So anyway, that weird number goes back to what's called a standard candle. And if you look at literature, even into the 1900s, there was a lot of work done to make literally candles that we agree that we're going to use this kind of whale oil and this kind of wick, and the wick will be, an inch long and blah, 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 and that'll be our standard candle. And so that's where this weird number comes from. And so this thing then converts watts times lumen per watts. It gives us the luminance, which has units of lumen per square meter steradian instead of watts per square meter per steradian per nanometer, because we basically have integrated over the nanometers and we've converted energy to this photopic thing. And there's actually, there's SI fundamental units for distance, meters, kilograms, seconds, etc. There's also an SI fundamental unit for brightness, which is called a candela, and that's 1 lumen per steradian. It's basically, we're going to have this standard candle here, and we're going to look at it and see how bright it is, a meter away and all this kind of stuff. So you can just keep in mind that an ordinary candle is, guess what, about 1 candela. But this candela is the SI unit. And when you actually measure that, it's done in terms of, you take platinum, you melt it, so you've got platinum at its melting point, and you look at it, it's like glowing really bright because it's like white hot. And you look at that and measure that, and that is the candela. The actual definition is that a pot of glowing melted platinum puts out 683 lumens, and that's how it all gets measured. Okay, so then, yeah, I think I've already said that. You know, you have a laser down here, you don't see it. Okay, so then here's just a little table of typical luminances. So the sun's roughly a black body at something like 5,800 degrees Kelvin. So, and here's the black body emission function as a function of wavelength, Planck's constant, speed of light, temperature, Boltzmann's constant, etc. So you can go to the web book, get this, use this to generate the radiance. So basically here's the radiance coming from the sun. We'll plug that in here, multiply by the photopic luminosity function, integrate over wavelength, multiply by our little conversion factor. So the luminance of the sun, if you go out and look right at the sun, and of course we don't recommend you do this, but if you were to do it, you would be seeing roughly 2 billion lumens per square meter per steradian. That's a really bright light. Now here's just a little table of other things. So here's our melting platinums, about 6 times 10 to the 5th lumens per square meter per steradian. A typical light bulb, you're getting maybe 100,000, you know, sunlit snow. Twilight sky is maybe 1 or 2 or 3. Heavy overcast, maybe 1,000, and so on down to like the darkest overcast sky, moonlit night in the middle of the forest, maybe 10 to the minus 5th. So there's a huge range of these things, but just for what it's worth. Okay, so you look at the back of a package of light bulbs. You're going to go buy a light bulb, and it will always say something like, brightness is 820 lumens, and it'll cost you $7 a year if you burn the bulb for 3 hours a day at 11 cents a kilowatt hour, blah, blah, blah. Well, you look at this and you say, okay, this is a, where does it say here? 60 watt light bulb, and I'm getting out 820 lumens. But Curt said there's 683 lumens per watt. So I ought to be able to get 683 times 60, that many lumens, and I'm only getting 820. So what's going on? Well, the light bulb here is at 2700 degrees K, and here's the black body radiation curve for 2700 degrees Kelvin. And here's the photopic luminosity function here, which is what your eye sees. So you basically take this curve, integrate times this function, and you can see that almost all of the energy being put out by an incandescent light bulb is out here in the infrared. It's not giving you light you can see. They're really, really inefficient. So if you're only getting 820 watts instead of 60 times 683 is 41,000, you're getting 2% return on your electricity bill for lighting your room. Now, of course, they're really good for heating the room, because go up and grab a light bulb, it's really hot. So if you just want to heat the room, yeah, buy light bulbs. If you want to see, you need to do something better, like LED lights. But even they're like 10% or something efficiency. So just another little example here. And then here's how you convert like an IOP to the photometric equivalent. So for, let's say, beam attenuation, so we know beam C is a function of lambda. We take that weighted by the ambient radiance times our luminosity function, integrate over wavelength, and then we take the radiance times the luminosity thing to scale it. So this takes beam C and converts it into the photometric equivalent. Now, it's kind of strange. Beam C is an IOP. It does not depend on the ambient radiance. But we've had to plug in the ambient radiance here is the way it's done. And so that makes the photopic beam C actually an AOP, because it does depend on the ambient radiance. And you could just think of it this way. There's a beam C out there whether there's any light or not. If it's dark, I don't see anything, so I'm not, You know, it's like there's not a beam C. So I plug in 0 for the radiance here. It's not defined. There has to be some light there for me to have a photopic quantity that I can see. Okay, so anyway, you can take any other AOP, absorption or whatever, and get an equivalent photopic thing, but it's actually an AOP. It's not really an IOP anymore. But it turns out, if you play around with this equation enough, that in many cases, this C sub V is really within a few percent of beam C at like 555. It's quite astoundingly good. So beam C at 555 is a pretty good approximation for the photopic beam C for average kind of daylight conditions. Okay, then we went through this radiance difference law, and you can do the same thing now starting with luminance, and you get a luminance difference law, which says the difference in luminance it propagates as e to the minus photopic C rather than beam C. So equation of the same form. And I also should comment that whenever I have a photopic variable, I stick a little V on the bottom to stand for visual. That's just a standard thing that people do. Okay, so you can look at this and say, oh, this is for luminance, not for radiance, because it's got the little subscript C's on everything. Okay, so then this gets us now into visibility as you see it with the eye. And so what we do here is we say, okay, if I'm right up close to a target and I see what the luminance is coming off the target, and I look right next to the target and I see what, let's say, the background water looks like, that's what's called the inherent contrast. So there's no distance between me and the object. So the visual or inherent contrast is the luminance of the target minus the luminance of the background divided by the luminance of the background. And that's the contrast at distance 0, or the inherent contrast. Now I back away and I still look at the object. I still look at a direction right next to it. And now I have a contrast at some distance r, which is the luminance of the target minus the background over the target, but now everything's at distance r away. Okay, so you can see here, if the target is brighter than the background, then this number is going to be positive. If the target's darker than the background, then this contrast will be negative. And then if there's no difference in the two luminances, then the contrast is 0. Okay, so then we get this thing called the law of contrast reduction. So here we're going to take, remember we go back to this guy, differences in luminances at R versus at 0, e to the minus photopic C times R. And so then we can take that equation and just rewrite it. And I wrote in, this was target minus background over background at distance R, and then I kind of just rewrote things. So now the contrast at R is the contrast at 0 and the ratios of the background at 0 and R, and then an e to the minus CR term. So that gives us this equation. This here is our inherent contrast. And then, well, it turns out that the background at distance 0 and the background at distance R, those are usually about the same. If the water's homogeneous and, I'm ignoring the effects of the object, then I'm looking at the water here and I look at the water back here, the water itself looks the same. So this part here is usually pretty close to 1, and I get that the contrast at distance R is just the inherent contrast seen up close, e to the minus CR. So that's this thing called the law of contrast reduction, or the law of contrast transmittance. So just like the radiance difference depended on e to the minus c, the contrast difference once again depends on e to the minus photopic c. Okay, so how this gets used, there's a little thing called Kohlschmieder's law. So he says, look, suppose we're looking horizontally at an object. It's a black target, so the inherent contrast is -1. In other words, we come back here and it's a black target, so this is 0, and then the background is something divided by that, so this term is -1. So he says, okay, if we have a black target, contrast transmittance is -1, that doing a bunch of experimenting, it turns out that most people can see something when the contrast is like somewhere like 2% or so. So he says, let's take this law, plug in that CR over CV is 0.02, and if we know the beam C photopic here, we'll solve this equation for R, and we'll call that the visual range. So the visual range would be, solving this equation, the log of the 2% difference divided by beam C, and that is about 3.9 divided by the photopic beam C, and this is pretty close to C at 550. So just a little rule of thumb is you can see something through the water at about 4 times whatever 1 over beam attenuation at 550 is. So you can actually go out and look and say, well, you know, I can see the bottom, it's like 4 meters deep, so this is 4 meters, that's 4 meters divided. Well, beam C at 550 must be somewhere like 1 per meter. Okay, and anyway, so this little law is just one of these rule of thumb things. Now, notice this is for a black target and a bright background. Well, if you have a bright target and a black background, things blow up, because if you go back here, the background is black, the target's not, and then you're dividing by 0, so this blows up. So then you have to go through a little different derivation, and you get this other guy's law, wherever it is here. Let's see. Yeah, anyway, so you have to do a different derivation, and you get Allard's law, and he did that to study how far can I see a lighthouse at night from a ship. So we've got the black background and the bright lighthouse. Okay, we don't need to do that here, but, you know, just keep in mind there's a whole like body of literature out there on all of this kind of stuff. And this is kind of what's used at airports when you're sitting in a control tower and they say, for the plane to land, we have to have a visibility of 1 kilometer, for example. They take the atmospheric beam C, they plug it in, and they say, you know, can we see that far today? And of course, if it's foggy, this is a big number, you can't see very far. Okay, so here's our Secchi depth business. So Father Angelo Secchi was a Jesuit priest. He was the Vatican's royal, or whatever, Vatican's papal astronomer back in the late 1800s. He did a lot of good stuff on looking at solar dynamics stuff, and a lot of stuff looking at spectra of stars. And this was back when you know, they were just learning to figure out, we can figure out what a star is made out of by looking at its spectrum and seeing if there's iron and calcium and all over it. So he was doing a lot of that, very good guy. And anyway, so he and the Pope decided to go sailing one day, and so Angelo said, well, let's stick something in the water and see how clear it is. So he cooked up this idea. He actually took a dinner plate from the Pope's galley on the Pope's yacht and tied a string on it and lowered it in the water to see how far he could see. Well, he got interested in this problem. In oceanography, people usually use a white disc about 30 centimeters in diameter. For some reason, people who work in lakes like to use a black and white disc, and far as I can tell, it really doesn't matter, but they get in big fist fights over which one's better. So anyway, be forewarned that some people will have a different Secchi depth for the same water depending on which kind of disc they use, and you just have to make sure you know which one is which. Okay, so the classic Secchi disc theory kind of works like this. You've got this disc in the water, it's illuminated by sunlight. So you've got light coming down everywhere. So that's ED, and ED attenuates with KD. But then the light hits this little disc, and only one particular beam goes back to where you're looking. There's no disc over here that can add in light, and if the light goes off in some other direction, you probably don't see it. So the idea is the disc is illuminated by an ED, or actually ED visual, and then it's the radiance, or actually the luminance, that gets it back to your eye. So that's attenuated by beam C. The light coming down is attenuated by KD. So that's the basic idea. And usually the disc is maybe 85% reflectance. So here's Preisendorfer back in '86, did this big review for limnology and oceanography and laid out all the theory and worked through it all. We're not going to go through that, but I put it here for reference from that paper. So you start out by saying the ED at the depth of the disk is the surface value, and e to the minus KdV. Then the value reflected here by the disk is the ED times the reflectance of the disk over pi. That's assuming the disk is Lambertian. We'll see what all that's about on Wednesday. Then you have a reflectance of the background water. You kind of do the same treatment there. You look at the inherent contrast of the disk as seen at depth Z, so you write down by the disk how much contrast is there. You turn that to a reflectance. You know, use the luminance difference law to propagate that up to the surface, blah, blah, blah. And then you eventually end up with an equation that looks like this, which is the Secchi disk. You suppose that if the contrast that you see in air compared to the contrast in the water, and you have to put in a factor for how much contrast is lost going through the wind-blown surface. So that's some number here, and people usually pick, once again, I don't know if I said it here, but usually this like 2% number. Anyway, so you basically end up with a Secchi disk depth is proportional to 1 over the KD to get the light down, plus 1 over the beam C that gets it back up, and then a factor gamma here that describes getting the contrast through the surface and what value do you want to use for how much the contrast has to be before the disk can be seen. And this number usually varies by like somewhere between 6 and 8, or maybe 6 and 9. Hydrolite uses a value of 8 here, and then you can run hydrolite. You get everything as a function of wavelength, like ED and LU. Then it integrates those things over wavelength, weighted by the photopic luminosity functions, gets an estimate of the KD and CV terms, and then it plugs those in and it gets the Secchi disk. But the catch is these numbers are averages from the surface down to the depth of the Secchi disk. But you don't know that depth, so you have to make a guess at the depth, compute the average KDs and Cs between the surface and the Secchi depth, plug it in here and get a first estimate, then go back and get a new estimate of the average from the surface down to the Secchi disk depth, recompute these, recompute this, and do a couple of iterations, and then it'll finally then come back and say, well, it's 8.3 meters. So that's what goes on inside hydrolite. Then I think that's what I just said there. And then Zhongping Li came around a couple of years ago and he said, well, I think this is maybe not really the right way to do the derivation. And so, first of all, this derivation sort of assumes the disk is very small and that it really doesn't perturb the ambient light field. And Zhongping says, well, the disk doesn't really have to be small. And he said that the visibility is not based on the target versus the background luminance differences, which is what's in here, but that it's based on the target and background reflectances. So it's a different way of viewing things. And once again, you read the literature, there are people who argue, well, it's really the difference in the reflectance of the surfaces that matter, and others will argue, no, it's really a difference in their brightnesses. But anyway, Zhongping said, well, let's see if we do the reflectances rather than the luminances. So he goes through, he does his little math, gets kind of a similar formula, and then he says, well, actually, we can replace beam C photopic with about 1.5 times the KD at some reference wavelength. And he comes up with a formula that looks like a little gamma over 2.5 KD, not KD photopic, the plain old AOP KD at some reference wavelength. Now, what's nice about this is you can get KD from remote sensing. So remember, a NASA standard product is KD at 490. And then from KD at 490, there's little models that give you KD at other wavelengths. So Zhongping said this formula is nice because I can remotely sense the KD and therefore remotely sense the Secchi depth. And so that's what he's up to in his analysis. So does his formula work pretty well? Well, here's from the CBAS data. He pulled out Secchi depths and RRSs, reflectances, and he's got absorption and scattering coefficients, and he estimates K from the absorption and the backscatter for a solar zenith angle of 30 degrees, and then he uses this KD to plug into his formula. And bottom line, here's the measured Secchi depth, and here's estimated by his little formula, and it's pretty good. Can't complain about that. That kind of fit's usually about as good as you'll ever see for anything in optical oceanography. So it seems to work. Now, what he didn't do, and nobody's done yet, but you can do after you get home, is a comparison of the Preisendorfer formula with the Lee formulas. And there's actually 2 versions of Zhongping's formula. So at the bottom of Hydrolite, there's 3 printouts of Secchi depth, one from Preisendorfer and 2 different versions of Zhongping Lee's formula. And they're usually pretty close. One will be 8 meters, one will be 9 meters, that kind of thing. And so, in all honesty, it may not matter much which one you use, but Zhongping Lee's is nice because you can get it from remote sensing. And so anyway, like I say, it still stands to have Zhongping Lee value versus Preisendorfer value with real data. Yeah.
Oh, we compared the Preisendorfer versus the 2 Lees for
Yeah.
your classic IOP case versus your new IOP case in Hydrolite, and your new IOP case had them a lot closer together.
Yeah.
The classic one, they were more variable between the 3.
Yeah, I can believe that. I've done those kind of simulations. I just haven't done it with real world data. So,
How would you really kind of test which one is correct, other than just try and collect data from the database? What do you think, where would they be most different? What would you expect them to be most different?
Looks like for Lee, this is Secchi depths, so they're very clear water.
I mean, one has 1 over KD plus C, the other has 1 over KD. So when would KD and C potentially diverge from each other?
When scattering is high and absorption is low.
So a good test would be in, case 2, in lakes, in places where things start deviating, even potentially in the lab. I mean, this could potentially be tested in the lab. You're adding your own scattering agent, thing that takes your little second on your camera. You can play with contrasted things and actually test it in a rigorous. Because open ocean everything covaries, or the other, you're likely to get stuff that's not going to be. As you get more and more places where scatterings and absorption and stuff deviating from each other, you might have a chance.
Okay, so then another viewpoint of the whole thing, Ron Zainefeld and Scott Pagao said, well, you know, if we really want to have some good measure of underwater visibility, rather than looking vertically at a Secchi depth, maybe you should be looking horizontally under the water. So they actually made a little gizmo that they had here at the class about 3 classes ago, where they put an object in the water here, and then they have a little periscope over here where you can look through the periscope and it looks out to the side, and then you move this thing away horizontally until it disappears. And so what they find is that the visibility range in meters here versus beam attenuation, they get this really nice little correlation here where they have a formula that says the visual range is 4.8 over beam C at 532, and this is beam C, not the photopic one. Beam C at 532 times 0.9 plus this, and that this is generally good to plus or minus 10%. So that's another way that you can use to get some estimate of how far you see something underwater. It's just a little less convenient because you have to have 2 people looking to like hold the target and hold the periscope versus 1 person looking down. Emmanuel.
Yeah, this is actually David Scully from New Zealand is the first to suggest doing this. I think from him they got and he published how to do it yourself. It has a huge advantage in rivers because Secchi depths, if you see the bottom, you cannot get an optical property basically. But if you can do it in a stream, and somebody just walks away from you and you look at the periscope until you don't see it. So I mean, it's easy to build. You can find online how to build a thing like this. Putting the periscope and putting the back.
Okay. Then there's this little thing called beam and point spread functions. Super important. So here's a fish tank. We're shining a laser out. If you're right up near the fish tank and you move the sensor right along here, it's pretty dark. The sensor's looking back this way. Dark, dark, dark. All of a sudden you're in this really bright beam, and then out here it's dark again. But as the light propagates through the water, it scatters, it tends to spread out, and somewhere down the road you see a beam that's not quite so bright, but then you have all of this kind of background glow of light around the beam. And that's basically called the beam spread function. It measures how the light spreads out from this initially collimated beam. So here's the way it's actually defined. You've got a source here putting out collimated radiance in this direction. And then you take an irradiance detector and you move it along the surface of a sphere at some distance r away, and you just measure the plane irradiance as that function of angle. And then you take the irradiance you measured out here at distance r, its angle theta, and you divide it by the emitted power here. So this is watts per square meter per nanometer, spectral power in watts per nanometer. That gives you this weird units of per meter squared for the beam spread function. Okay, that's the way that's defined. Now, kind of thinking about this reverse Monte Carlo thing, instead of having a collimated source and a plane irradiance detector, suppose we have a plane irradiance source and a collimated detector. Well, then we have this. We have a source here that's sending out an intensity now, so intensity is power per unit solid angle, but it's going to send it out in the little cosine pattern, and that light will bounce around, and we've got a collimated detector that's looking in this direction, angle theta and r, and some of this light, of course, will scatter around and go into there. And that's called the point spread function, because we've got a point source and we're seeing how that kind of spreads out. So the way that's defined is you take the power of the source and divide it by pi here, and times the cosine of the angle that it's emitting light. So for theta equals 0 to pi over 2, it's emitting light out in this direction, and then it's not emitting any light out the back. So if you define the intensity this way and you integrate over all solid angle, then the total power emitted is P, same as in the previous case. And then to define the point spread function, you take the radiance detected divided by the power over pi, and you get the same units here. Okay, so then, well, here's, if you're looking like at a street light and it's a little bit foggy, so here's a street light and there's this kind of glow around the light. Well, there's our point source. It's not really quite a plane irradiance emitter, but close enough. And then the pattern of this glow of light around the street light is simply the point spread function seen from whatever distance where you are. Okay, so here's data going back to 77, back in the days of the visibility lab, of the point spread function measured according to its definition, the beam spread function in blue measured by its definition, and these were on 2 different days in the Bahamas. So beam C one day was 6.8 meters and the other day it was 7. So it wasn't quite the same conditions. But you look and you say, well, you know, many orders of angle, orders of magnitude of angle and of magnitude, those curves look really the same. So there was this big debate for a long time, what is the point spread function equal to the beam spread function? And once again, fistfights would break out at ocean optics conferences over it is or isn't. But then Howard Gordon finally said, enough. He sat down, did his Howard Gordon kind of radiative transfer theory, and proved that these are indeed exactly the same thing. Okay, so funny story here. Well, funny story first. So back in '98, when Paula Bontempi was in the class, and I gave a lecture like this, and she said, well, I don't need to know anything about point spread functions and stuff because I'm a biologist. Then she takes a job at NASA. Like day 2 on the job, they say, you got to go to this meeting about the MODIS instrument. And she goes to the meeting, and the whole meeting is about the MODIS point spread function. And it's like, oh, I guess, Curt, you know, I really should have paid attention to that lecture. So anyway, you'll see why that's true here in just a second. So here's just some simulations. Here's Fournier-Ferrand phase function, Petzold, Fournier-Ferrand for biology and for minerals. And then I have a Monte Carlo code where I trace photons and I come up with point spread functions and beam spread functions. Now the thing about the volume scattering function is it tells you the angular distribution of light for one scattering. The beam spread function or point spread function tells you the effects of all the scattering and absorption between your source and where you observed it. So the beam spread function, if you wish, is a lot of volume scattering functions screwed together till you finally get to the source. So that's the difference. So here's beam spread function all normalized to 1. There's low index of refraction and high index of refraction, and then different optical distances, 1, 10, and 30. So you can see here the low index refraction particles are doing a little less scattering than the high index refraction particles, and you have a little bit difference in the shape of the beam spread functions. And there is close to the target and then further away and further away. So that's just an example of what these things look like. And you can see they look sort of like a volume scattering function. And at a tau